Hello, everyone. Welcome to our online conference hosted by Mate Maroc. Today's topic will be about the mathematical connections between control and machine learning. But before we dive into our topic, I would like to introduce our speaker. Today we have with us Professor Dr. Enrique Zuazua, who is the head of the chair of Dynamics, Control, Machine Learning, and Numerics at Friedrich Alexander University in Germany. Professor Zuazua got a degree in mathematics in 1984 from the University of the Basque Country and a dual PhD degree from the same university in 1987 at the Université Pierre et Marie Curie in Paris in 1988. During that time, he had the opportunity to collaborate with the well-known professor Jacques-Louis Lyons, who had a huge impact on his research. In 1990, he became professor of applied mathematics at the University of Madrid. Professor Zuazua was awarded several prizes, such as the Euskadi Basque Country Prize for Science and Technology in 2006 and the Wright Prize of Siam in 2022. He has also been the principal investigator of several funded projects, among them three ERCs and one Humboldt professorship. Professor, thank you very much for accepting our invitation. The floor is all yours.
Thank you. Thank you very much for this kind presentation, this invitation. For me, it's a great honor to be with you in this Moroccan network. Morocco, a friend country that I visited for the first time when I was a bachelor student at the University of Basque Country, and since then I had the opportunity to come back again and again many times, where I had so many friends and collaborators. So in the last 2-3 years, we had the opportunity also and the honor to host here in Erlangen with us Dr. Ilyas Eftui, one of the most brilliant young applied mathematicians from Morocco. And I'm very pleased to have Ilyas here in our family, and through him the opportunity to talk today to all of you. So yes, this is a lecture that will be not very technical. Maybe it's late in the evening also to get very deep into mathematical proofs. But I would like to somehow share with you my enthusiasm for this topic in the interface between control and machine learning, where many, I will say most of the know-how we have developed during, say, 50, 60, 70 years after Second World War, right, and the emergence of computers, we have developed in the context of applied mathematics. So this area, so my first statement is that control and machine learning, two disciplines that might seem to be different from, an external observer. My claim is that they are very close. But of course, to argue, to justify that they are very close, we have to find the bridge. We have to find the path to connect them. Okay. So let me just show you. This was advertised. This is a paper published in Nature last week, actually, where they talk about the digital twins for the energy of the future for plasma fusion. As you know, until now, the fusion of plasma was being handled. Well, it still is, it's an experimental process that is developed in accelerators and tokamaks, right? And the mathematical aspects of the technology were handled by classical mathematical modeling, numerical analysis, and dynamic control processes. In this new paper, the breakthrough is that this time, all this know-how accumulated so far, right, is being enhanced by the use of reinforcement learning, by machine learning algorithms, with the aim of developing a digital twin. So what is a digital twin? A digital twin, of course, can be applied in many, many different contexts. This is a technology that will become ubiquitous, universal in the coming years, decades. So the digital twin can be, just a small gadget, like a program in our cell phone to monitor our health, or can be, a sophisticated computing laboratory where we integrate data We can simulate in real time. We can, try to guess new strategies, predict behavior, singularities, and so on for all kind of technologies we can think of. Right? It can be, meteorology. It can be electrical networks. It can be astronautics. Any application you might have in mind. Until now, this was done also, right? This was the goal of classical mathematical computational mathematics and applied mathematics, right? But nowadays, the great advantage is that one, we have very powerful computers. Second, we have information in real time to many data, and we have the opportunity to process them in a real time manner using all the know-how we have developed in applied mathematics together with these new ideas in artificial intelligence, like in particular in reinforcement learning, where oftentimes we are ready to quit, determinism. We are ready to quit the classical paradigm in which we want to approximate the solution exactly, and we are content by doing it in high probability because, after all, we know that life is random, right? So, but as I said, so digital twins is a fantastic technology of the future. This will be developed in all possible fields we can think of: automotion, aeronautics, personalized medicine, sociology, politics, sports, everything, right? But as I said, uh, conceptually, from a mathematical perspective, what is really, giving a sense and a possibility of these new technologies of being really efficient and performance is the fact that several fields of applied mathematics can merge and can actually interact in a, say, satisfactory manner. As I said in the beginning, the goal of this lecture is to bridge control and machine learning, something that plays an essential role on developing these digital twin technologies. And in order to do that, I would like to start by showing you two videos. So these are two simulations done in our team. On the left, you see a classical control process in which four dogs in blue are herding a flock of sheep, right? So you see that the dance, this intelligent motion of these four dogs in blue, has pushed the herd of sheep to move from the original destination position to the destination, right? Just by avoiding the proximity of the dogs. On the video of the right, now you see three populations evolving with three different colors, like yellow, purple, and green. And you might think, well, so maybe this is also a herding problem, except that now there are three species of animals. There are not only, sheep in red. There might be maybe dogs, cat, and horses, for instance. No, this is not a simulation. The second one is not a simulation of collective dynamics of animals. It's just the dynamic representation of the behavior of a deep neural network that we interpret as a dynamical system, either discrete on time or continuous on time, doesn't really matter. But when we produce the video, we see, of course, a time continuous film. So first on the left, control theory, second one on the right, machine learning. But now let's think how this video belonging to the field of machine learning was produced. What did we do? We had three categories of items to be classified. It doesn't really matter what it was. It was just dots in the Euclidean space with different colors. And we wanted to classify them. We wanted to gather them by subgroups. We wanted to bring all the yellows with the yellows, all the greens with the greens, and all the purple with the purple. The same we do when we are putting order in our photo folder in the computer. We open the photo folder in the computer, we see we have 10,000 photos, and we want to put order on them. You can do it by year. You can do it by persons. You can say, oh, this is my dad, my mother, my sister, my brother. I generate a folder per person, and then you try to classify them. If you try to do it by hand, well, you will probably classify 50, 100. I guarantee you will be tired. So what do? Then you use the capacity of the computer to do the job for you. So you identify some of these photos with the names of the persons under consideration. And once this is done, you ask the computer, please cluster the photos, please organize the photos, and you will see that rather successfully, not 100%, but with a great level of success, the computer will be able to place every individual in the corresponding folder. Of course, this will not be 100% success. It will be maybe 97%. You will check the folders to verify that everything is in order. Maybe you will have to recolocate by hand the few 300% photos that are badly collocated. And actually, by doing this, you will observe that the computer, maybe in the folder of your brother, has put your own photo. So what does it mean? It means that these two persons look alike. And of course, the computer was confused the same way as persons can be when you are not really able to distinguish, for instance, two brother twins. Okay? So now on the right-hand side, this was a deep neural network with the goal of realizing this typical objective. The first objective, in data science is classifying data. And how did we do it? Well, this is the so-called supervised learning paradigm, in which, as I have said, you put labels, you name some of the, of the items, and then you train a deep neural network with the goal of classifying properly these items that have been labeled. Training the deep neural network means adjusting the parameters in this dynamical system, discrete or continuous in time. And how do you do that? Well, you do that through optimization techniques. So after all, when solving this machine learning problem, we have used the ideas and the tools of classical control and optimization. The only reason why we don't identify this video on the right with the classical field of control theory is because on the video on the right, I didn't draw the evolution of the parameters of the deep neural network. I could have done it, and then you will have seen these blue lines oscillating, giving you the values of the most relevant parameters, and then I could have argued, you see, on the video on the left, sheep were the particles to be controlled, and the dogs were the controllers. In the video on the right, these items we are classifying like photos, right? Or patients on a hospital or students in a university. These items we were classifying were the state, and the parameters of this dynamical system that we generate through machine learning ideas are the controls. So the two fields really merge, right? And not only they merge because these videos look alike, but actually there are mathematical models that build the bridge I anticipated in the first slide. So one of the most paradigmatic models that links classical applied mathematics with machine learning is the neural differential equation on the top. In this neural differential equation, we see the state X is one of these items that is evolving in the space of images. Is typically a very high dimensional Euclidean space because every image is made of many pixels, and each pixel is one coordinate in this huge dimensional Euclidean space. But of course, the model can also work in any other Euclidean space dimension, 2, 3, 4, 5, why not? In this dynamical system, right, the time derivative of this particle, this item that we are collocating, is evolving in the space of images, is driven by this right-hand side, in which you identify, on one hand, parameters W, A, and B that depend on time. They are the controls of the system. And you also see a very peculiar nonlinearity, sigma, which is the so-called rectified linear unit, which is nothing but, the function that is 0 to the left and linear to the right, so the function x plus. Very nice piecewise linear and Lipschitz function, the so-called rectified linear unit or ReLU. You say, well, this is a strange nonlinearity, so, this is probably because people in machine learning have, different ideas of what the nonlinearities one should employ are, because when I open the book in mechanics, I typically will encounter, nonlinearities that are quadratic, like in Navier-Stokes, or maybe sinusoidal, like in the sine-Gordon equation. Okay, good. Now, this ODE, of course, is nothing but the continuous version of this discrete version on the middle, in which we have just discretized in time. And now when you see the discrete version, you say, well, but this is really a neural network. This is actually a residual neural network. Why residual? Is because in every step, I'm moving from the position xk to xk plus 1 by just adding a small increment that is due to the influence of this nonlinearity through the chosen parameters. And then when I observe this, and I then see that, oh, this is just a way of accumulating in a time-like manner, right, what the classical ansatz in neural network does. For instance, if you go back to the classical paper by Sivenko in 1989, you see that using the Hahn-Banach, theorem as a corollary of Hahn-Banach, as an application of Hahn-Banach, he is able to prove the so-called theorem of universal approximation, which in machine learning simply means density. What Sivenko proved is that the ansatz below, in which I combine k times, this sigmoid or ReLU activation function with different choices of the parameters, is dense in the class of, say, L2 functions locally in space. Oh, this is a new density result. We knew already Stone-Weierstrass, polynomial functions are dense. We knew Fourier series are dense. Say infinitely and compactly supported functions are dense. Finite elements are dense classes. This is a new class of dense functions, right? And this statement, was the one that led, to, in particular, these kind of results were the kind of results that motivated this very fast growth of the mathematics of machine learning, because people said, after all, well, if this function is dense, if this class of functions is dense, whatever I want, I can approximate it by an object of this form. In particular, if you see the cloud on the right, where I have red dots and blue dots, and I need to classify, these two categories, basically what I need is to define the characteristic function of the blue dots in the space of the reds, right? Then, this characteristic function indeed can be approximated by this kind of ansatz. And because of that, we can reduce the problem to identifying the coefficients Wj, Aj, and Bj that do the job. Of course, also together with the number k of neurons I have to put on these ansatz, because, of course, as usual, density is achieved only when you put more and more and more term on your series. Now, one aspect that is very relevant in this context, and which is different with respect to other approximation paradigms, is that this ansatz of neural networks belongs to the category of nonlinear approximation theory. Why nonlinear? Well, because the function, the output of this series, depends nonlinearly on the coefficients Aj and Bj through the function sigma. Now, what do people do? They say, listen, we know now neural networks develop, are able to generate classes of functions that are dense. So whatever you ask me, I can do it with these functions. So, experts adopt different, architectures for the neural network. You can put many layers, right? You can make them very wide. You can make them very width. You can choose the architectures you like. You can make the dimension going up and down as in an accordion. After all, the problem is about, to identify these coefficients W, A, and B for each neuron so that your task is achieved. And if the task was to classify items, if the task was to bring the initial data into the corresponding labels, well, I can just do this using a least square strategy. Just minimize, right? And guarantee that the coefficients that are chosen are those that minimize the collective distance of the items with respect to the corresponding labels or locations. Of course, as indicated on the right-hand side, right, to guarantee that the problem is coercive, you will add some penalization term a la Tikhonov. Now, this is fantastic. We have reduced the problem of learning to an optimization problem. There are, however, some issues that are delicate. One of them is the course of dimensionality. This was anticipated by Bellman in the context of control, right? So Bellman was a genius. He realized, you have to solve control problems as when we are sending a rocket to the moon, right? You want to solve a control problem, you have to optimize the trajectory. The trajectory will be optimal if you are optimal at any time, right? And then the control will be given in a feedback manner, except that this feedback will be complicated because you have to solve a Hamilton-Jacobi equation. And then what Bellman claimed was, well, intellectually we know how to do that. In practice, we cannot do it because we face the course of dimensionality. There are so many possibilities, so many options that in practice, for a human, it's impossible to make the right choice. And this is why computer scientists and engineers, based on the ideas of Bellman, they bifurcated from the mathematical research that was very much about, gaining understanding on this nonlinear Hamilton-Jacobi equation through the analysis of viscosity solutions and so on. They said, let's be practical and let's try to do our best to deal with the course of dimensionality. The second difficulty we encounter while solving these problems is that, as I said, the dependence of the function, the ansatz on the coefficients is nonlinear because of the presence of the activation function sigma. And this means that these loss functions, even if I put squares everywhere, they will not be convex. And as you know, when you are dealing with the lack of convexity, again, optimization is very difficult. Okay? So now, what can we do as mathematicians? Well, what we can do is to first admire and recognize the breakthrough that, this field developed. They were, for instance, able, using these ideas of reinforcement learning and Bellman dynamic principle, but recognizing that this was not, we could not solve it completely deterministically using random-like, Monte Carlo-like ideas for exploring the universe of possibilities. They were able, for instance, to develop the machine that defeated Kasparov in in chess game, or more recently, the world champion in Go. Or last year, the company DeepMind developed new algorithms to multiply huge matrices that are more efficient than those that were known before. So as mathematicians, what we can do is first recognize the great success and then try to understand and explain. And hopefully, if we explain and understand, right, we will be able to improve also and make some of these methods to be less, energy consuming, to be more robust, and to be more reliable, right, and less complex. So, of course, there is plenty of work to be done. There is at least work for the next generation of applied mathematicians worldwide, I will say, because in particular, the number of architectures in neural networks is so huge. Each architecture has been developed for a different goal, right? Because it's not the same architecture for a large language model like ChatGPT as the one you use for solving, a standard low-dimensional optimization model. So there are so many different architectures and so many deep questions that there is really plenty of work to be done. This is something we have been doing in our team for the last 4 years or so. When COVID started, we needed something new to work on, to spend all these months on confinement. And this is when we started playing with these ideas. We have written a number of articles. I advertise here some of them. And in particular, I would like to, invite you to have a look to the first one, which is a short 2 or 3 pages dissemination article that I wrote in the newspaper Siam News in the fall 2022, and where you will see an abridged version of the talk I am giving you here. Now, let's get now deeper. What's control? Well, control starts, basically developing substantially with the Industrial Revolution, right? And back in 48, when Norbert Wiener defined cybernetics, automatics, control theory, control engineering, he tries to give a definition. He says, this is the science of control and communication in animals and machines. And then you wonder why this is not also the definition of artificial intelligence, right? Because all we are trying to do, both in classical control theory and in artificial intelligence, is to, build machines that will be able to do the work of humans so that we humans can do something else. So this is why nowadays, right? 25 years ago, we started having, Google. And then if I was interested on some mathematical concept, like for instance, approximation theory, I could Google, and then I will probably get to the Wikipedia and then see what approximation theory is. And then, I start clicking in the Wikipedia and I can see some of the main references and the differences between linear approximation theory and nonlinear approximation theory and the historical origins and the applications. But now, 25 years later, I can just use ChatGPT, these large language models developed by artificial intelligence, and ask more precisely to ChatGPT to say, listen, ChatGPT, good evening. Can you please help me? I would like to know the basics about approximation theory in mathematics. In particular, I am interested on the historical origins, the main applications, who were the main contributors, and which are, say, the key results that I should keep in mind in order to have a vague, at least a first idea of this large and fantastic field. ChatGPT will do it for me. And all this happened because of the mathematics we are talking about now. Let me show you one of the fundamental results in control theory, something that everyone understands. So it's how you control a linear finite dimensional system driven by a matrix A. So this can be, for instance, a social network. This can be the math Morocco network, right? So maybe 200 colleagues interested in applied mathematics. They are interconnected. They are communicating maybe by WhatsApp or so. But of course, the connectivity is not the same among all individuals. Some of them simply read. Some others are, the influencers that are sending the information. There is a connectivity matrix A in this network, okay? And then we want to control this network. We want to bring people in today to this lecture at 7:30 p.m., and this is where, the organizers and the influencers, the coordinators impact, introduce input in the system. They send messages, they share information through the control operator B. Now the question is, can I control a large dimensional system, right, where all these particles and agents are interconnected through the matrix A, by just acting on some of the nodes of the system, maybe just acting in one of the nodes, God controlling the whole system. Can this be done? Yes, this can be done if and only if the rank of the matrix B, AB, up to A, n-1B is equal to the dimension of the system. So there is a purely algebraic condition that tells you whether you can do it or not. So then, yes, there can be a God. There can be a God where just by one single control, right, controls the whole system under the condition that, the control operator B is designed, is chosen so that this rank condition is fulfilled. The fact that this condition is fulfilled means that somehow this control operator B has been chosen so that the trigger effect is guaranteed, so that you just, with your magic finger, you touch one of the nodes, but all of them are interconnected, and then one after another, they will all obey the orders that were introduced by the control U, so that the whole system get into the desired state, which is all together here today at 7:30 p.m., right? Now, you see, this is a marvelous mathematical result. Everyone understands. You just need linear algebra to prove it, okay? And basics about differential equations. Just know what the exponential of a matrix is, right? By power series expansions. But now the question is, I am really satisfied by this result. Now, I give you a system, driven by a matrix A, 200 by 200, because we are 200 people in this network, right? And then I ask you, can you tell me whether the system is controllable? Then you will say, well, listen, Enrique, I'm not really interested on solving this exercise because I have to take this matrix A, which is 200 times 200, and I have to multiply by itself, 200 times. And then once I do that, I will have this huge matrix, B, A, B, up to A, N minus 1B. And then you will ask me to compute the rank of this matrix. And this is a painful linear algebra exercise. For moderated sizes, of course, I can do it using even MATLAB. But for big sizes, this is where you see, I have to use tools like the ones devised by DeepMind that help me multiplying matrices. And then I see that I am back to artificial intelligence. So what we are experiencing now is kind of a loop, right? We have developed control theory, and we claim that the control theory, mathematical control theory we have developed will help machine learning. But even when we try to do that and transfer this know-how into practical applications of machine learning, we realize that we are obliged to deal with these huge computational problems, the course of dimensionality anticipated by Bellman. And to do that, we need machine learning again. And this is how things will develop in the future. There will not be any more traditional applied mathematics on one hand and machine learning and artificial intelligence on the other, but the two fields are merging, and they are merging in order to tackle the great challenges of humanity, like, for instance, fusion of plasma. Okay, but this is how classical control theory works. Now, you ask me, can you park a car? I tell you, yes, of course. I have the driving permit, but I have learned also control theory, and then I can do it optimally. You see, this is the optimal way of parking a car, done mathematically, computationally, using the tools and the ideas of control theory. And I think you will all agree that if we had to do this exercise in practice, probably we will not get in the first shot, the right optimal strategy. Most drivers will need a few iterations to do what in principle can be done in just one shot if you choose the optimal control strategy. Now, how did I produce the video in the beginning about herding 4 dogs herding a flock of sheep? This was done in a series of papers, in particular with Ramon Escobedo and Dogman Co. Ramon Escobedo now in Toulouse and Dogman Co. back in Seoul. And what we did was to write a large system of particles in interaction. We assume that all sheep are the same, which is not true in general, but just to simplify the model, we consider that all sheep have the same behavior, the same mass, and so on. And what we made was to pay particular attention to the fact that dogs are modeled differently because, of course, the behavior and the mutual relation between sheep and dog is very different. Sheep are afraid by the dogs, and the dogs are attracted by the sheep. And this asymmetric motion is the one that permits herding, right? How did we compute the optimal strategy? Well, of course, we used ideas of control and optimization theory, but in practice, these complex dynamics I have shown you had to be developed computationally. And in order to do that, we combine the random batch method, which is a kind of a stochastic gradient descent method to make the computation lighter, together with model predictive control that in principle was designed to cope with errors in models, because in practice, of course, any mathematical model is always insufficient to really, mimic the reality. So control theory has also adopted this strategy of model predictive control, to be able to improve models, along the control process by learning from errors and from perturbations. And this is what we did, and this led to the video I have shown you now. Okay, but now let me go to the second part. Assuming we have already know a little bit of control theory, and we understand that the herding problem can be solved, how did we solve the second problem, the second video in which we classify items? So I show you a very simple example. This is something that everyone understands. Classifying trash. Plastic goes to yellow. Glass goes to green. Paper goes to blue. Organic goes to gray. Everyone can do that. We can all do that, but we don't want to do that. We don't want to spend our time, classifying trash. So we would like a machine to be able to do that. And what is a machine? A machine is a robot, but this robot has to be driven by an algorithm. And behind this algorithm, there has to be a mathematical program, a mathematical function. So eventually what we need is a mathematical function that will take every item and put it in the corresponding reservoir, in the corresponding container. How do we build this function? We say, well, this is precisely supervised learning. I have here 32 items in this collection. You see 32, 8 per category. And then I put the label. I go to the, 8 plastic, I say yellow. 8 glass, I say green. I can put the labels. So I have objects in the domain of definition of the function, and I have the labels in the space of, the image of this function f I'm trying to build. Now, how do I put this in the context of Euclidean context? Well, it's very easy. For instance, the labels, these 4 labels, I can put it in R2 on the Euclidean plane. I say simply south, north, east, and west. And now, how do I put these objects into the Euclidean space? Well, I will take with my cell, I will take photos, Every photo is just a collection of items. And in this way, every object is in a high dimensional Euclidean space. So supervised learning consists on building a function that is mapping these objects from the domain of definition into the corresponding labels, and doing it nicely, right, without too high oscillations, without overfitting, so that later, right, when you use this function for classifying another object, this object spontaneously will go to the corresponding basket. And this is exactly what the computer does when is classifying the photos in your phototheque, right? Or Ilias knows, because he lives with us here in Germany. When you go back to the to the supermarket in Germany and you have the bottles at home, empty bottles at home, you can bring them to the machine and you get money back. And the machine is very smart, because you get 25 cents for the bottles of plastic and 8 cents for the glass bottles. But the machine never makes mistakes, right? So the machine, you put a bottle into the machine and immediately the sensor detects whether it's, plastic or glass, and then you get either 25 or 8, but it's very, very hard to cheat the machine, okay? And now, what did we do? We said, well, this function that we are aiming to build, we will get it by using control theoretical ideas applied to this, residual neural network, this neural differential equation I have presented in the beginning. So then the problem becomes like a huge ensemble or simultaneous control problem in which I have to choose the coefficients W, A, and B in this ordinary differential equation, so that I guarantee that every item spontaneously gets to the corresponding basket. And this is the video that was done by our former PhD student, Borjan Geskowski. Now is a researcher in INRIA in Paris, and this works. Now, why this works? Well, it works because you can prove a theorem, right? So don't read this theorem. It's written in Science Review last year. in collaboration with Dominic Ruiz-Ballet, now postdoc in Imperial College London, also a student in our team. In this theorem, we say, listen, in any space dimension, Euclidean space dimension greater than 1, 2 or more, because in one, two particles, they cannot cross without colliding. You need room, as you have in 2D or in 3D, to classify, to generate a sufficiently complex motion. In any dimension, give me any number of items n, give me any number of clusters m, I will always be able to find a control that is classifying these items, and this control will be piecewise constant with a finite number of jumps. In particular, the control will be BV in time, bounded variation, and therefore the ODE, which is driven by a nonlinearity that is globally Lipschitz, it will be perfectly well posed. How do we do that? Well, it's very simple, actually. The proof goes by induction, right? And relies essentially on the nature of the neural differential equation. And very particularly, it relies on the fact that the nonlinearity sigma in this ODE is this capricious ReLU. You recall the ReLU was sigma was 0 to the left and it was linear to the right. What does it mean? Well, let's see. Assume you have chosen some controls. I don't mind. I let you choose the controls. So you choose the controls WT, AT, and BT. By the way, let's clarify the dimensions of this system. As I said, X is your image or object you are trying to classify. So X lives in a high dimensional Euclidean space RD. So X dot on the left is a column vector, right? It's a column vector of D components. W, the control W, is also a column vector, which depends on time. Sigma is just a scalar, it's just a number. So sigma is a number multiplied by W, which is a column vector. But now, how is this sigma evaluated? Well, sigma takes values on the scalar product of A dot X plus B. So it means that A is also a vector. So you have the scalar product of the vector A and X. This gives you a number. And B is also a scalar. So is a scalar number that is simply translating the sigma to the left and to the right. But you see, the critical point of sigma is the 0 one. Is the one that splits left equals 0, right linear, right? Identity. So what is the equation A dot X plus B equals 0? The equation A dot X plus B equals 0 is the equation of a hyperplane in space, which is perpendicular to the vector A, and that has been translated by the value of B. So what I'm actually doing when I am controlling the system and making choices of A, B, and W, which are strategic, I'm doing the following. At every time t, you have a big knife, and you are cutting a space into two halves, according to the directioning of A and B. At any time, you cut a space into two halves. And then you have the half, to the left of this interface, like in the picture down, in which, because A dot X plus B is negative, then sigma is 0. And if sigma is 0, of course, sigma times W is 0. And then X dot is W, the derivative of this photo, of this particle, is 0. It means this particle doesn't move. So with this neural differential equation, what we succeed is that at any time, half of the space is frozen. And what does the other do? Well, the other half space in which A dot X plus B is positive, sigma is linear, so you can just drop sigma. Then you get a linear ODE, so you get an exponential response of the system, and this exponential response will be oriented in the direction of the vector W. So the game is, with one hand, you are cutting a space into two, and with the other one, you are just pushing in the direction of W the half space that is active. And my claim is, if you combine these two motions, cutting and pushing, in a strategic manner, you will be able to classify any finite number of items and drive them to the destinations you have chosen a priori. How do we do the proof? We do it by induction. And it's the same principle as in the Rubik cube. So you see on the left, on the Rubik cube, you see a Rubik cube that is disordered. And on the right, you see a Rubik cube that has been solved. Why do we say that the Rubik cube has been solved? Well, we observe the picture on the right, and we see that every face is homogeneous in color. In the beginning, the microfaces, the green, the blue, the white, the red, they were totally disordered. But now when I look on the right, I see that in the big faces of the cube, I have full homogeneity of color. In one of the faces, only yellow. In the other face, only blue, and so on. So what do we do for solving the Rubik cube? We know that we have to do a finite number of manipulations. Of course, the world champion does it in 4 seconds. For us, doing it in 1 minute is already a challenge, right? So you see that there are many ways of solving the Rubik cube. And normally you are successful if you are able to find one of the paths, probably not the optimal one, but it's the same problem as in control theory, right? Where we have seen how easily the computer parks the car, but in practice, we know that any driver will need more motions than that in order to succeed to get the car to the corresponding location. So in the Rubik cube, we do a finite number of actions, and in each action, half of the cube is frozen while the other one rotates. You see the analogy with what the ResNet is doing. In every time step, half of the space is frozen and the other one evolves in the corresponding direction. So A and B decide which part of the cube is frozen, and W determines in which direction the other one is rotating. Okay? And now, in order to convince you that this can be done, let me just show you in this toy exercise that, of course, you could do it yourself. As I said, the proof goes by induction. And induction means I have essentially to do one kick and then learn that whenever I have classified n items, I can classify one more, n plus 1. Let me show you how I do one of these kicks. So here you see 9 dots, 3 blue, 3 green, 3 red. And then, of course, I have the labels, the blue, the green, and the red. And then I say, listen, classification means that you have to take the 3 blue and put them in the blue band, the 3 green in the green band, and the 3 red in the red band down. You check and you say, well, there are 9 in total. Oh, the exercise is almost done because there is only one blue that is badly placed. I have to take this blue, which is in the middle of the green band, and I have to put it in the upper band in the blue. But recall that we are doing an induction procedure. So, of course, I have to take the blue and put it with the blues, but without undoing the good classification of the other 8 that I already did until now in my induction procedure. So the 2 blue in up will stay there. The 3 green in the middle have to stay there, and the 3 red down have to stay there. How do I do it? Well, my claim is that I can do it by the procedure I told you, using a neural differential equation in which the coefficients A, W, and B will be chosen just being constant in 4 different arcs. So it will be like a switching control strategy, right? And to make it simpler and easier to understand, what I will do in this case, I will not use all the possibilities I have, but to make it simple, I will just use the W's that push the system either, up and down or horizontally, so according to the Cartesian axis. And also the cuts I will avoid using oblique and complicated cuts. I will just use horizontal and vertical cuts. So now you see the movie. In the movie, you will see 4 motions of this configuration. In each motion, you will see a dark part. The dark part is the one that is frozen. And you will see the bright part, which moves in a direction that you will identify. So first motion, left frozen, the right goes up. Second motion, down frozen, the up goes left. Third motion, up is frozen and down moves left. And last motion, left frozen and right goes up. So you see, what did we do? Our goal has been to take this blue and put it to the most right. Because if this blue is here, we're here, it will be very easy to classify. I just do a vertical cut and I push the right part to up. Unfortunately, the blue is in the middle. Okay, I would like to put it to the right. How can I do it? Well, I cut here horizontally and I push these three to the left. I cut now here down horizontally and I push these four to the left. But unfortunately, and this is why in this example we have taken these two dots horizontally aligned, if I do that, still the green will be to the right of the blue. So what did I do in the first motion? What I did in the first motion was to cut here and push the right up so to break the alignment on the green and the blue. Because once I break the alignment of the green and the blue, the previous algorithm I have told you works in 3 motions. I needed total 4 because I needed simply to break this alignment. If this green has been here up, 3 motions will have been sufficient. But because they are aligned, I need here 4. And you see it again in the video. The first one just pushes the green a little bit up, and then you have the horizontal cuts to isolate the blue one to the most right. And once the blue has been isolated to the most right, you cut vertically and you push up, and that's it. Okay, that's it. So now this opens a fantastic perspective because we have understood supervised learning and this in this architecture, right? Using control theoretical ideas. Then there are, of course, many other architectures. There are, for instance, the so-called deep non-residual neural networks. This is a topic that, our PhD student Martin Hernandez has solved. Similar ideas can be applied to, deal with this more nonlinear, more complex dynamical system. And again, using the discrete dynamics that deep non-residual neural networks develop, you can understand how a space has to be cut and how these cuts are generated by the proper choice of the coefficients in the deep neural network architecture. And then eventually you succeed once again, for instance, in this case, classifying all dots of 4 different colors into the corresponding locations so that all the blues are with the blues, all the green with the green, all the red with the red, and all the brown with the brown. There are many other topics to be investigated. A work that we have finished recently with the PhD student Antonio Alvarez and Arsalan Aj, that was now he's a PhD student in Paris. He was an internship student last spring in our lab. So what we did was to explain how, you can exchange the depth of the network by the width, right? So you see in the ansatz on the top now, I'm not using just a single neuron. I am combining P of them. And what we have shown in this paper is how when you make the deep neural network to be wider and wider and wider because P grows, like in Sivenko's original static ansatz, then the controls, because you are combining many motions, P motions in every step, of course, the complexity of the control diminishes and you pass from N into N over P up to the limit in which the dynamical system can become autonomous. This is a joint paper with Antonio Alvarez and my colleague Rafael Oribe in Autónoma de Madrid, where we say, listen, the algorithm we have developed with Domenech is perfect, except that it is prepared to deal with the worst case scenario. But in practice, normally when you take dots, randomly, you will encounter that there are clusters. And whenever data are clustered, of course you can classify much faster because you don't need to bring dot by dot, but you can take clusters, the same we do with our hands, right? You can take, you are eating grapes, you don't need to take grapes one by one, right? You can just grab a few of them all together, right? So we can use the capacity we have of identifying clusters to classify with less complexity. A topic that is now being developed also in our group by, in particular, Siki Wang and John Kun Song is federated learning. This is a very important paradigm in the applications in machine learning because there are many of them in which several, say, participants will collaborate in order to learn better, but under the condition that they don't share data. For instance, medical applications where different hospitals will collaborate in order to develop, better methodologies for the diagnosis of any illness, right? They are ready to cooperate, but of course they cannot release confidential data of the patients that are really, according to law, something private and that needs to be, gathered carefully within the hospital. The same if different car companies are maybe ready to develop a new technology together for, the braking in autonomous cars, right? They will be happy maybe to collaborate, but certainly they will not be willing to share the main features that constitutes the advantages of each of the companies. So this is kind of a control problem. We can view that as a control or optimization problem in which we can use the classical ideas of splitting, domain decomposition, and alternating descent, but with the drawback in this case that you cannot transfer information across the interface because of these privacy considerations. And finally, there is a very interesting link of this theory with the theory of optimal transport because you see, after all, right, what did we do? We dealt with these ordinary differential equations. Ordinary differential equations are just characteristics of transport equations. And what we have done is we have shown that we can build ordinary differential equations that are able to bring data from whatever initial configuration you have given me to any final configuration, which is precisely the goal of optimal transport. Except that here, I didn't discuss optimality in the sense of Monge and Kantorovich, right? In their context, they try to minimize, the energy spent in the transport map. Here, what we do, we say, well, maybe our transport map is more expensive, right? But it has a great advantage, right? Because it is very simple to be computed. It has a very, very simple geometry because at every time is just given by this Rubik cube idea in which I cut the space in half and the other one moves in the strategic direction. So this is the end. I thank you again for your kind invitation. I'm open for discussions. Of course, also to, you can exchange with me anytime in the future. And I invite you all to try to read more and work in this area that is fascinating and in which there is so much to be done from all perspectives, from all math perspectives, probabilities, dynamical system, control, numerical analysis, approximation theory, right? Nonlinear approximation theory in particular, with this goal of developing the new methodologies of the future, in particular, to be able to develop these efficient digital twins for those questions that concern our society. Thank you again, and keep in touch.
Thank you very much, Doctor. I think we have some questions from our audience. The first one we have here: in your opinion, how can mathematics follow the fast evolution and development of artificial intelligence tools?
So can you say again the question?
Uh,
So it was a bit generic, right? So
yes. In your opinion, how can mathematics follow the fast evolution and development of artificial intelligence tools?
well, that's a very good question. Actually, when we started thinking on this 40 years ago, 4 years ago, right? 4 years ago, I got here in Erlangen. Here in Erlangen, we have companies like Siemens, Puma, Adidas, Schaeffler, and there is a lot of interest in our university in technological transfer, artificial intelligence. This is often driven by computer scientists and engineers. And I said, well, how can we contribute to this? And then, of course, when you approach this field, you are frightened, right? Because there are so many papers emerging every day. You have to find a path. And the path, somehow, as indicated there, you have to build it from where you stand. So, if in our case, it was easy because we were experts in dynamical control theory, and these topics are really very close. It could well be that you are an expert in probabilities, right? Then this has to be your standing point and your approach. You have to say, well, I approach the field of machine learning is huge. There are many topics I don't even understand, right? Many papers that are written are even hard to read for us because after all, we are mathematicians, right? But I
Yes.
know probabilities. And I know that there are some topics, in machine learning that are being tackled by probabilistic methods. Like for instance, given even when you tune your deep neural network the best you can, the deep neural network will not be 100% successful, and then you will claim, well, how can I estimate probabilistically the success rate I can expect out of this neural network? So my recommendation is, if you are interested in working in this field, whatever you have done so far, do it from this starting point. So there are some people that say, listen, I am a numerical analyst doing partial differential equations. Well, then you can start figuring out how these machine learning ideas can help you on your work, and also how your ideas in numerics of PDE can contribute to this machine learning topic. For instance, some people what are doing is they say, listen, I will use all my know-how in numerical analysis of ordinary differential equations to produce new neural networks. You know how I will do it? I will take the neural network you give me, because it's very hard to understand. I will write down the dynamical system underneath. And once I build this dynamical system, I will now apply the Runge-Kutta methodology I like. And this will give me again some discrete, time discrete dynamical system that I will reinterpret as a neural network. So everyone working in any field can contribute to this. My recommendation is, do it from your own area, and little by little, in interaction and in discussion with other colleagues, try to learn more and try to explore a little bit more, right? But this is like doing tourism. I mean, you get to a big city like I don't know, Marrakesh, Paris, or New York. Yeah, I mean, you can be there one weekend, you can be there 1 week. You will not see all the interesting corners of the town, right? This is something that you will have to explore little by little.
Yes. And we have another question here. How does the Kalman observability criteria apply to nonlinear systems?
Well, there is a whole theory for this, right? So in that case, for nonlinear system, you have rather to do Lie brackets, right? But then you get similar results, right? You can understand whether a nonlinear dynamical system is controllable or not by checking at any point of the phase space whether the vector field generating the system and the vector fields that the controls provide, by computing the Lie group they generate, whether this group has full dimension or not. Yeah, that's a very good question. But this is something that is much better understood. Of course, there are some technical problems that are not yet completely solved mathematically, but this is something that is part of the folklore of nonlinear control theory.
Yes. And what are the main challenges in applying machine learning algorithms to control systems?
Well, so there are two things, right? So what we have done mainly is to use control theoretical ideas to try to explain why machine learning works. Then the other way around, the way you formulate the question is, how do you use machine learning for control? And this is what is being done through reinforcement learning, right? But still, in reinforcement learning, many of the methodologies are heuristic. There is plenty to be done to mathematically analyze the convergence of these reinforcement learning algorithms, and of course to develop new reinforcement learning algorithms that are more efficient. Yeah.
And finally, we have could you briefly state some current research trends at the intersection of machine learning and control theory?
Yeah, so this was the goal of the last few slides. So federated learning is certainly one of them, right?
Yes.
Very much related to multi-agent systems, game theoretical problems, and so on, right? Of course, there are many relevant issues here to be understood because, in principle, when a federated learning exercise is organized, there is a server that is coordinating, and there are several clients, several participants. But it could also be that one of them is a hacker, right? And then, of course, you have to develop, cooperative strategies, but that are sufficiently intelligent to detect the possible presence of one of the agents that is aiming to contaminate, right, the process, right, because he has some spurious goal. So game theoretical ideas are very present there. And as I have mentioned, another very interesting topic is the link between, optimal transport theory as developed by Mons Kantorovich, right? And then in the last few years, further developed by many people, in particular the last two Fields medals we had in applied math, like Figali and Villani, right? Optimal transport theory versus the dynamics of machine learning deep neural networks. That's, I would say, these are certainly two fantastic topics, but there are many others, of course.
Yes. And do you think can we improve the performance in multitask network using control theory?
Multitask network.
Yes.
What is a multitask network?
What is a multitask? I think the person who asked the question will tell us more about the
Yeah,
multitask
I mean,
network.
of course, I understand. Multitask network is what? I mean, we can guess that is a neural network, right?
Yes.
That we have designed, right, with multitask with different purposes, right? So maybe I build a robot that
Yes.
is able to classify trash, but simultaneously, I don't know, is able to what else? To it's a cash machine, so that I can get money from it, right? So
Yes.
of course we can think on this kind of dynamical systems, right? That
Yes.
are sufficiently complex, right, so that they are not only able to to deal with some dynamic properties, but also with others, right? So this is like, for instance, just to give you an example, partial differential equations. What will be a multitask partial differential equation? For instance, thermoelasticity is a multitask partial differential equation system, right? Because you have the wave component and you have the heat component, right? So the acoustic waves are propagated, or the elastic waves are propagated, but also temperature is diffused, right? And there is an interaction between the two. Of course, if you are, dealing with a multitask process, you are willing to build a deep neural network that you aim to be multitask. You can already use all your know-how of dynamical systems and partial differential equations, because in particular you will have to clearly understand what are the different dynamic regimes, right? And you will have to tune the parameters so that in each of these regimes the system performs optimally. Yeah. So I will say that multitask deep neural networks will be very close to the typical goals we have in traditional applied mathematics when we are dealing with multiphysics, right? The same, for instance, for fluid structure interaction, right? Two objects put together in the same model.
Yes, thank you. I think we did every question. Thank you very much, Doctor, for your time and
Thanks to
for your
you.
great questions. Thank you very much,
Thank
uh,
you.
and see you next
Thank
time.
you again. It was
Thank
my
you. Bye.
great pleasure and honor. See
Thank
you.
you.
Bye bye.
Thanks.
Ciao.